Hello. In today's video, we are going to be talking about discrete random variables or discrete probability distribution functions. Your goals for this lesson is to be able to define a discrete variable x for a given scenario, determine the possible values of x, as well as their associated probabilities. Secondly, can you use a formula or scenario to calculate the probability of all the possible outcomes? And can you create a probability distribution table from a given scenario? In the second video, we're going to come back and look at what expected value is. So let's jump right in. Let's imagine we have some counters, in a jar. There are 6 counters in total, 4 blue and 2 red. You draw a counter at random, and without replacement, you then draw a second counter. So just given the scenario, let's just try and create a tree diagram to model what is happening. And the reason why I'm choosing a tree diagram in this case is because there are successive events. You're drawing one counter and then you're drawing another counter. So let's set this up. The first column will be the first draw, and then the second column will be the second draw. The possible outcomes is blue or red. And then we're going to add branches to these possible outcomes as well as their associated probability. So there are 4 out of 6 blues and there are 2 out of 6 reds. Notice that all the probabilities in this event sum to 1. Now, if you were to then draw a second counter, again, your possible outcomes are blue and red. But this time, all our denominators are going to change to 5 because you've already drawn one counter. Okay, assuming that you've selected a blue counter on the first draw, there were 4 to begin with, then there are only 3 left out of 5. And then for the red counters, you haven't drawn a red, so there's going to be 2 out of 5 remaining. Assuming then that we draw a red counter on the first try, there will still be 4 blues left in the second draw, but only 1 red left on the second draw. Okay, so here's our tree diagram, and we can see all our possible outcomes. So let's list them out. We could have 2 blue counters, and to find that probability, I'm going to take 4 out of 6 and multiply by 3 out of 5, giving us 12 out of 30. Okay, or the second outcome, second possibility is blue followed by red. So that's 4 out of 6 times 2 out of 5, which is 8/30. We could have red followed by blue. And again, we multiply across the branches of the tree diagram, giving us another outcome of 8 out of 30. And then finally, what's the likelihood of drawing red followed by red? That's 2 out of 6 times 1 out of 5, which is 2 out of 30. And if we sum all of these probabilities, notice that they do add up to 1. Okay, so let's now link this to a discrete random variable or a discrete probability distribution function. Let's first define some of these terms. Okay, the word discrete means that there are distinct or separate countable outcomes. A random variable is simply a function that assigns some numeric value to each possible outcome of a random experiment. So in the example of coin flips, your random variable might be that you're trying to figure out the number of heads or the number of tails that come up in your coin flip experiment. It could be the number that appears on a dice roll. It could be family size, so anything that can be counted. An example of something that is not a discrete random variable would be a continuous random variable, so things that are measured. Usually that's things like height, weight, mass. And what is a probability distribution? Well, that is just a sample space that shows all the possible outcomes and how likely each one is. And this can be expressed in words, as a table, or algebraically. So if we look back at our counters example that we just set up the tree diagram for, and then change it and represent it as a probability distribution, we might say, let x be the number of counters. So our random variable is x. We don't know exactly which outcome we're going to have when we go in and make the draw. There could be three possible scenarios. Either you draw two counters and none of them are red, in the case x is equal to 0. You could have x is equal to 1, where one of them is blue, or you draw two counters and both of them are blue. Okay, and so you can see that the lowercase x represents all the different values that our random variable can take. In this case, it could be 0, 1, or 2, the number of blue counters. Then, where we have p of x is equal to, then in the case where we have p of uppercase x is equal to lowercase x, that's where we represent their probabilities. So there's a few important things to note here. The first is that the sum of all the probabilities in your probability distribution function must equal 1. And so what we can do is write that as the sum, so this is the Greek letter sigma, of p of x is equal to lowercase x is equal to 1. Over here, this symbol or this expression represents the probability that the random variable takes on this particular value of x. So why are these useful? Well, for one, they can help us answer questions about what is the most likely outcome and what we can expect on average. Let's now look at a few practice problems together. A magazine store recorded the number of magazines purchased by its customers in 1 week. 23% purchased 1, 38% bought 2, 21% bought 3, 13% bought 4, and 5% bought 5. Let X be the number of magazines purchased by a customer in a week. A. Construct a probability distribution table for the random variable X. And B. Find the probability that X is greater than 2. I'm going to invite you to pause the video now and see if you can work this out on your own. What would the probability distribution table look like for this random variable X? What values can X take on? Okay, so let's try this together. Okay, so for our lowercase x, customers can purchase 1, 2, 3, 4, or 5 magazines. Now what we want to do is attach probabilities to each of these lowercase x values. So 0.23, 23% purchase 1, 0.38, 38% purchase 2, 21% or 0.21 for 3, 0.13 or 13% for 4, and 0.05% or 0.05 or 5% purchased 5. So here's our probability distribution function as a table. If we add all of these probabilities, they need to sum to 1, representing our entire population. A quick check, we can see that in fact it does sum to 1. And now we can use this table to figure out the probability that the value of x is greater than 2. So I'm looking for the sum of these three probabilities. So the probability that x is greater than 2 is equal to 0.21 plus 0.13 plus 0.05. Well, 0.21 plus 0.13 is 0.34, and then add another 0.05. That gives me 0.39. Before I move on to the next worked example, now would be a good time to pause and try these two questions that you see on the screen here. Here are the answers. Okay, so let's take a moment to pause and think about what we've done so far. So far, we have defined what a discrete probability distribution function looks like. We were able to generate a table using verbal description, and we were able to also answer questions about the probability function given the table. Next, what I would like you to do is try the next three questions that I show here on my screen. So here's a medium level question where you're asked to create the probability distribution function given the algebraic representation for it. Here's a hot level question of the same vein. And finally, here's another one involving words, and it's asking you to also create the distribution table as well as look for the mode of your random variable. This is a good time to pause, but if you do want support for these questions, I'll see you in the next video. Okay, but first, remember to try them on your own.